So this is our polarity testing. Polarity testing is one of the tests that are required for the initial testing of the installation. Because of when we are doing this installation, before you do anything, we have to switch on, we have to test the polarity. So in this case, polarity test will verify all switches are installed in the system are connected in the current carrying connector and not in the neutral. So this means that all the connectors are connected in the current coding. Because of the all switch must be connected to the current carrying connector, but not at the neutral. Therefore, that we have to check whether connector has been connected at the active or neutral. We have to check. Because of if you isolate the switch, neutral circuit via the single pole circuit breaker or switch will appear the circuit dead. So this means that all those you did the circuit dead, but circuit is still alive. So this is the thing. In this case, if the polarity is not correctly determined, there will be risk of the electrical shock during the maintenance procedure. Because of when you switch on this neutral, electrical current is still on this terminal, so that it can leukemia electrocuted. So this is this polarity testing. Firstly, you have to check this visual inspection. By using the knowledge and the sight and the correct termination of the cable related to the core colors can be established. In this case, the red is a active or the red or brown are active, yellow, black are the neutral, blue grays are also the active, and black is also black blue are the neutral. This is the color coding principle. So the polarity check visually during the process of installation. So when you are install the electrical system, you have to check the polarity. Now this is the polarity by the continuity testing. In this case, this is the supplies are at here connected to the switch at it. And that is a show that we call the polarity. Supply neutral switch neutral must be indicated. So this is for we are using the polarity testing. In this case, we have to choose a temporary link, have to remove, and you have to test the polarity. So this is the ways how you check the polarity with the ohmmeter. So that we use as a testing using a low resistance ohmmeter. So what you have to do is you have to switch on the circuit breaker, supply circuit, but you have to switch on the supply. And from this specific circuit, put the temporary link that connect the connector and the CBG or exponential bonding connector. So in this case, you have to connect this temporary link. So this is what you order supply, and you have to put this temporary link. So this is you put a temporary link like this. So here we see the active terminal connected here, temporary link we join, and we have to test. So the one terminal here, another terminal here. So you have to test. So this one is also this one you have to test, this one you have to test. So from the specific circuit, put a temporary link. So this is we put a temporary link. Then we connect the line connector and CBC or any exponential equal potential bonding connector. It will start as testing point for the convenience. So this is you have to test the temporary link. You have to switch on everything, you have to do the temporary link. So the conduct the continuity testing by placing the test lead across the connector and near the CBC or any expo. So this is the one on the connector here and the expo wire you connect it. You have to test it. If the instrument shows the zero reading, the switch connected to the polarity or line connector. So its equipment might show the zero. Hello? So the one is a continuity test. So we have to check the one continuity here to another here. So this is the supply, the wire go to the switch, the district terminal and the supply active terminal. They must show this continuity. And although this after this one neutral and other there's a low output, then we also be you have to check. So the conduct continuity testing by the placing the test lead across the line connector and near the CBC or any expo connected power circuit. If the instrument shows a zero reading with the continuity sound, then the switch connected properly to the line connector. If the instrument shows the 1 second which is ohmic value, That switch is not connected to the line connector in the chain connection to in the physical program. So this is the way you have to check and then you have to correct the thing. So this is the integer checking on the continuity is a one terminal here and another here you have to check. And the continuity test R1, R2. So this is R1 plus R2 continuity test. So this is the R1 plus R2 continuity test and you have to check that and read it. Now this is a live testing. Two methods are not possible due to urgency. We got found a live polarity testing by using the approach body. So here is a live testing the test between line and neutral terminal. You have to check the line and neutral terminal. It might show the body. And test between neutral R terminal, neutral R terminal. And this is a test between the neutral R terminal. This is neutral terminal R terminal. We see. The test should not indicate a full body to the niveau between the line and neutral line. And the instrument should indicate full body. If you connect the line and neutral, this one must be the 230 volt. But line to up, there must be the 0 voltage. So this is the line full voltage, line to neutral, line to up. No voltage between the neutral and up. So this is light testing. So this is the light testing system. While we do require that we perform the test on the low voltage installation before they are connected to the supply. Because you have to do the low installation, then you have to before you connect to the supply. But do they really matter? Will it really affect the installation? They waste the time. Many electricians feel that they are not worth for their time. So the important because of we have to test the continue of the other system. Possibly that this ensure that hard acid is suitable to ensure that the fuse circuit breaker will operate before the piece of body. Because of if the hard acid continuity, when the output happens, circuit breaker will open. Otherwise, circuit breaker will not be working. Insulation resistance is also important. If this is too low, then we raise the equipment are independently becoming the live. So that when there are the insulation very low, the equipment can be live. So the fires and the overheating from the leakage currents and the equipment damage of the electronic circuit can happen. Polarity also important. We need to ensure the active neutral and the R wire are in the right position because active neutral R must be right position. That's the matter. Yes, the swap the AE and risk delivering the free of the piece equipment, somebody can die. So this is also called circuit connection also important. Ensure that the circuits are not suitably connected in such way that may cause a safety hazard or incorrect operation. Because of if the circuits are incorrect, it can happen the fault. Follow impedance is also important. This is associated with the corridor. The wiring mandate that under the fault maximum voltage of the 50 volt can exit on the piece of the equipment for the no longer 0.4 seconds before circuit protection operate. So therefore, before the circuit protection operate, so then 50 volt must not exit longer than 0.4 seconds. The next one is the operation of RCD. Under the wiring rule, RCDs are currently required to be fitted to the starting circuit where if been deemed to save or the no more than normally. They like to be concerned. So they also the RCD also when the electrical output happen, RCD must operate. So that you can see this one of the video for the testing.
So at the final stage of our basic lighting circuits, we've extended it from one-way onto two-way, and now finally onto two-way and intermediate. And as before, we're going to carry out the continuity of CPC test and polarity. We're going to follow it off by the insulation resistance, and then our circuit is going to go live, and we're going to do some basic live testing, recheck polarity, does it work, and functional testing, do the switches open and close the circuit. So before we start, we've got to do the continuity of CPC test, set the instrument up as we've stated previously. So I've set it onto the ohm scale, which on the Mega MFT is in the orange scale, and we're going to need to remove the resistance of our link. So we've stated this in previous video presentations. I'm going to link together the crocodile clips, which are in the red and green sections in the top of the instrument we've talked about before. The instrument automatically starts, so we're reading an ohm reading now. Press the test button. So we've got a reading, press the test button again, and we've now gone to 0. Remember, if it's flashing 0, it's below 0. We need to press the test button at least one more time. So we're going to link together now in the consumer's unit the line, conductor and the earth bar to pick up the CPC. So we're linking together the line and the earth bar, and we're going to go and test the furthest point on circuit, which, believe it or not, is the lighting point. Just to remind you, the line conductor comes through into the loop, comes down on our twin brown, and then works its way through the switching line conductors, depending on which configuration we're in, until it returns back to the lighting point, making the maximum amount of cable being at the lighting point, and it is the furthest point on circuit. However, we record the highest reading wherever we achieve it, and we should see when testing at the lighting point that our reading will change depending on how much of the switching circuit we have in. So we only need to make a mental note of the highest reading at that lighting point before we drop down to do continuity at the switch, middle switch and last switch. So we're going to do the continuity CPC at the light fitting as usual, checking polarity at the same time, does it come on and off. Remember the highest reading, drop down to each switch in turn, again remember the highest reading and record whichever reading that is. Under our box heading R1 plus R2, R1 representing the resistance of the line conductor, R2 representing the resistance of the CPC. If it does come on and off as we go through the switching sequence, we can also tick the polarity box, and then we can move on to our insulation resistance test once the covers have been reinstalled. So let's get on with the continuity of CPC and polarity combined test next. So we're going to connect on to our earth terminal, which is securing into position our circuit protective conductors, and we are going on to the switching line within the actual band lamp holder. We discussed previously why we're not coming in here. We've only been here 7 weeks. So I'm onto my switching line within my batten lamp holder. I'm currently in the on position with a reading of 0.54 of an ohm. Hopefully we can turn it off now. So I'm gone greater than the scale, so I've got full scale deflection. Turn it back on. I've now got slightly less at 0.51. Back on. Now we've got 0.55 and then off again. So I've run through from first switch through and then back again. I don't operate each switch in turn. You turn one off or on, whichever way it is, and go to the next switch and back again. I need to leave the circuit in the on position, so let's turn it on at any switch. And our reading is the highest one we've achieved of 0.57. 56. And we've proved that these switches turn on and off the light fitting itself, so therefore we've proved polarity, but we've still got to prove continuity of CPC at each individual switch, and whichever reading we get, wherever it is, we will record the highest one. So we've got about 0.55 of an ohm as our highest reading. Let's do it at each switch in turn next. So I drop down to my first switch, and I just need to pick up a line conductor and the earth terminal where the CPC.
To beat right is on solar. Soak up more sun, more energy, more money on bill, and right.
CPC is connected, and I've got a reading of 0.29 of an ohm, which is lower than the reading I achieved above. So we now move to the second switch. So we come to the second switch, which is our intermediate switch. We're going to pick up the line connection and connection for the CPC. And we've got a reading of, settles down, 0.23 of an ohm, which is lower than the reading we achieved at the lighting point. We move to the last switch, which is a two-way switch. Again, we pick up a line and the CPC, and we get a reading of 0.27 of an ohm. So we have achieved the highest reading in circuit at the lighting point. We've proved polarity by operating the switches and leaving them in the on position. We're now ready to move on to our insulation resistance test once we've put all the covers back on and ensured that all loads are removed. So let's do that next. So we've completed our continuity of CPC and polarity test. We're ready to move on now to our insulation resistance test. As stated before, we need to turn our instrument into the mega ohm scale and set it to 500 volts DC. We've also inserted, as before, our leads into the green and red sections of our mega MFT. Once again, we could have used the blue lead, but we've chosen to use the red and green lead. We're going to short the leads together to ensure that we have continuity of those leads, so we should get a dead short on the insulation resistance test. We have, proving that the leads themselves, and I said they can snap here without actually seeing them physically snap, they can come disconnected there. So we've proved we have continuity of our leads by shorting them together, and we're ready almost to start our insulation resistance test. We must ensure that our switches have been left on. We did during the continuity test, and we've got, in this case, they're all down. That doesn't need to be for two-way and intermediate, the down throw to be on. They can be in any combination of up and down. But we've left them on during the continuity test. We must remove all loads, so the lamp itself needs to be removed before we start the test, and also any sensitive electronic devices. In this case, we've got the RCCB. We must ensure that that is in the off position, and we must ensure the circuit breaker is also off, because we said before the test doesn't need to go out and do the circuit, and actually pass it back through the circuit breaker and across the bottom of the RCCB. So the supply is isolated. We're ready to do the insulation resistance test, so let's move on to that test. So there's no particular order in which we did the test, so I'm going to clip on first of all onto my earth bar, and I'll test between that and the top of the circuit breaker, trying to keep my arms out of the way, and press the test button. And we've got a reading of greater than 999 mega ohm, so off the scale of the machine. And I'll go across and do between the earth and neutral bars, press and test and hold it on, greater than 999 mega ohms. Now I'm going to go between my neutral and my top of my circuit breaker for the line, so neutral and line. Once again, I've got a reading greater than 999 mega ohms. We expect the overall insulation resistance of our consumer unit, that's all the circuits, to give us a reading greater than 1 mega ohm. Further investigation is required where the reading falls below 2. Brand new installation with only one circuit. We expect it to have a fantastic reading for insulation resistance. We don't expect the insulation to have deteriorated through time, through age, through sunlight, so UV degradation. And perhaps it's been connected to something very hot. We don't expect it to be broken down over time. We've got a brand new installation. Our insulation resistance should be fantastically high, somewhere in the hundreds of mega ohms. However, the test is not complete, as our installation has two-way and two-way intermediate switching. So we've got to walk back into the installation now and throw once again both two-way switches into the opposite on position in order that we test the other part of the strapper. So let's do that next. So we're not quite complete our insulation resistance test yet. We need to walk into the installation and find our two-way switches and throw them back into the opposite on position in order that we get the other strapper in circuit, and then do the insulation resistance test for that circuit again. So as we come into our installation, we've got a two-way switch, intermediate, and a two-way switch. It is only the two-way switches that need to be thrown into the opposite on position. It wouldn't matter how many intermediate switches I had, we'd leave those alone.
Off here and back on here, and now I can go back to my consumer's unit, and for that circuit repeat the insulation resistance test again. So we come back to the consumer unit after throwing our two-way switches into the other on position. This is in the strapper in circuit, and again I'll go onto the earth bar, top of the line, press and hold my instrument, reading greater than 999 mega ohms, onto my neutral bar, so earth and neutral bar, press and hold the test button. Reading greater than 999 mega ohms. Move across, I'll do between the neutral and the line. Press and hold. Got a reading greater than 999 mega ohms. I've now completed the insulation resistance test because I've done it in both on positions. If I had 10, 20, 100 intermediate switches, it's still just the two-way switches that are thrown into the opposite on position in order that we get the other strapper in circuit and complete the insulation resistance test. So now we've completed the continuity CPC and polarity test. We've done the insulation resistance test twice. Did it in the first on position. We walked out into the installation through both two-way switches and then repeated the insulation resistance test again. We're now at the point where we're going to go live. We only do very basic live testing. We check it works again, and we're calling that rechecking polarity. Does the light come on and off? I'll show that in another video presentation, and prove the functionality of the switches. Do these switches actually turn on and off the light fitting? And have we got the ability that the glorified switch, which is the RCCB, operates from on to off? And our circuit breaker also will open and close the circuit itself, seeing it go on and off. So they're glorified switches in the consumer unit, and we'll pick that up on functional testing. I hope this video has been some.
So the next one is insulation resistant test. So this is why is insulation resistant. Insulation resistant is we have to measure because of the when the insulation breaking down, the fault can happen. So this is why we have to protect. So the insulation resistant IR test measure to the resistance between any 2 points triggered by the electrical insulation. The test therefore determines how effective the dielectric is at resisting the flow of the electrical current. The minimum acceptable value of insulation resistance is 1 mega ohm for each 1,000 volt. So this is the insulation resistance.
His time and aircraft donations fuel the country.
Hey YouTubers, and welcome to this tutorial video on insulation testing. Now in this video what we're going to do, I'm going to go through some analogies and the theory of insulation testing. We're going to talk about the various test equipment available to do this testing, and then we're going to go through some actual practical examples, and I'll show you how to do some insulation tests and the results to expect. Now the reason I'm doing this is because I have a whole host of equipment from various manufacturers which I hope to do video reviews of in the near future. So having this as a good background will help you appreciate the features on these pieces of equipment. Right, so in this video what I want to cover off is obviously insulation testing. It's also known as pack testing or mega testing. Now the pack testing is derived from an acronym, portable appliance testing, and that's something that's specific to the UK, Australia and some parts of Europe, where the law mandates that particularly appliances in public places like hotels or shops, or some places even in the homes, needs to be tested to ensure that it is electrically safe. Now there is specific pack testing equipment for that, but the theory behind the pack testing is very much an insulation test to ensure that the insulation is working correctly in it. The other name I mentioned is mega testing, and mega testing comes from in part mega ohm, which is the measurement result you look for from an insulation tester. Also the company Mega, who produce test equipment to do insulation testing, their name has come that renowned that often people won't say they're going to do an insulation test, they're going to do a mega test on some electrical wiring or equipment. So during this video, as I said, we're going to have a look at insulation testing, both an analogy and the theory behind it. We're going to talk about safety because that's very important. We're going to have a look at the conditions and pre-checks that you should take into account before you do any of this testing. We're going to have a look at the types of leakage current because that gives you an understanding of the types of tests you might need to do. And then we will have a look at the types of tests, both proof, spot, predictive, step, DAR and PI. And then we'll talk about insulation in electronics. Right, before we do get started, I do want to give a big thanks to my sponsors, one of those being Barry of tester.co.uk. He supplied the Unity tester down at the end and the metal tester down over here. And then Paolo of Isotech, who supplied the Isotech insulation testers. Without them, these videos wouldn't be possible, so certainly do consider looking at their links below and supporting them. I know Barry of Test.co.uk in particular, his company, because he's based in the UK, they do specialise in some pack testing equipment and information that's related to that kind of testing. Right, before we do get into the meat of this video, the one thing I do want to just highlight and ensure you understand up front that doing insulation testing is a very specialized area. It can be very dangerous and needs to be carried out by someone who knows what they're doing or is certified to do that kind of work, particularly an electrician. By watching this video, don't think you're going to be armed to be able to go and do this kind of testing yourself. It is very dangerous. It could potentially be fatal. So although I'm going to go over some of the safety aspects, perhaps we'll be missing out some of the important criteria, but you just need to be aware that this isn't going to arm you to go and do this testing yourself. Right, so why would we want to do an insulation test? Well, it's to check the insulation on our electrical wiring systems. Inevitably, over time, what can happen due to either damage or moisture or contamination, you can have your electricity leaking out of your conductor, out of your wires, into places it shouldn't go. Now, at a nuisance level, that can cause issues. For instance, in your house, you may find that during certain types of weather, particularly when it's raining, you may have your lights tripping or your electricity tripping out because moisture is getting into a wall, and that is enough to allow electricity to jump out of a conductor and trip a switch. And that's a nuisance factor, but nonetheless there's an issue there. You could have, as I said in the case with a portable appliance, something like a kettle which has got a metal housing on the outside. If you have an issue with the insulation, if you have a live wire touching that metal casing, when someone goes to use the portable appliance like a kettle, they could receive a nasty, if not fatal, shock. So what the insulation testing does is send a test voltage down through your electrical system to see if there's any leakage current which is going to pass through the insulation of the wiring of the appliance or the machinery. Now, in order to do that, what the insulation testers do is they will send a higher voltage than standard in most cases to pressure test the wires to see how well they behave. A good analogy of that is literally the plumbing in your own home and the water, and perhaps a test that a plumber would do when he's building a house to check that the pipes aren't leaking. So here we go. Here I've got a pipe with a pressure gauge on it and a pump at the end. The pipe is closed. Now this is important. So let's say our plumber is in your house. He's just gone and put in all the new plumbing inside a new house, and the plumber wants to ensure that it's not going to leak. Well, if the plumber just applies the municipal pressure to the piping might be fine, and it might not reveal any weaknesses or leaks in the system. So to properly test it, what the plumber needs to do is to apply a larger pressure than perhaps the municipal water system is going to apply to force out or highlight any weaknesses in the plumbing or the fittings and see if there's going to be any leak. So what he would potentially do is obviously have the higher pressure put on the pipe, which is closed off. He would need to ensure that there are no taps or faucets that are set to run. It's the same with an electrical test. If you have some lights or equipment on the electrical system in the circuit, those can affect the test results. And so those are the checks you need to go through to make sure you're going to get a good result and it's not going to be upset by clippage you've got on the pipe or the electrical system. So if we had to pressurize this pipe, just like you do if you apply a voltage, which is pressure, we would let the pressure gauge go up. If there were no leaks, in theory, for one, we don't want to see, he wouldn't want to see any water leaking out of the system. But how you'd be able to tell that is to ensure that the pressure gauge is reading at the same pressure that he's applying. And in the same way, when you do a pressure test on an electrical system, what we do is we apply a higher voltage, and our pressure gauge is to measure the resistance. This is where Ohm's law comes in very handy again. Because as we know from Ohm's law, resistance is equal to your voltage over your current. Now, I've already said our test equipment is going to supply constant pressure or a constant voltage, and that's what the insulation testers do. So if we've got a constant V, but a change in any way in I, then we're going to see a change in R, the resistance. So I is a flowing current. So if you can imagine, if there was a little leak in this pipe and we had some water leaking out of the pipe over here, what you're going to see is a drop in the water pressure. And likewise, in an electrical wire, if you happen to have a little bit of current flow, while you're applying your constant voltage, you're going to have I with a value which is going to drop the value of R. The resistance value is going to be lower. Whereas if you have no current flow, your resistance is going to be high. So ultimately, when we're pressure testing our electrical systems, what we want to see is a high resistance value. Those resistance values which determine whether or not a system has got good insulation or not will depend on the type of system you're testing and at the voltage you're testing at. Now, understanding the types of current flow that you can get is very important to understanding the potential types of tests you need to cater for and the things that can upset your readings when you're using an insulation tester. Just like understanding the different types of leaks you might get in a water pipe and how those will affect a pressure reading, we need to understand the different types of leakage current. So we've got three of them. The one is, we'll call IL, is conductive leakage current. We've got IC, which is capacitive charging leakage current. And then we've got IA, which is polarization absorption leakage current. Now, the conductive leakage current is something that naturally occurs in all conductors with an insulator. Your insulator or dielectric is never going to be perfect, and you're always going to have some leakage through the insulation. That is ultimately what you want to measure, is to understand what that leakage is. But it's the other two types of leakage currents which can potentially upset that reading. That leakage normally will be in the order of microamps. And of course, the one important thing to know is that in a test like this, we use a constant pressure, which is DC, direct current. And alternating current in this test is not going to help. You want a constant pressure, and that's why these tests with the insulation testers are done with DC. Now, the capacitive charging leakage current will happen in certain situations. As you know, if you've got two conductors next to each other with an insulator or dielectric, you're going to have capacitance. And what happens when you charge a capacitor with DC? You can have an initial flow of current, and it's going to taper off. And that's important to note, because if you just try and do the quick check with an insulation tester and don't account for that, your initial reading might not be correct. So over time, if you look at this little graph I've got over here, if you're charging a capacitor, you're going to have that initial run of current, which is going to give you a lower resistance reading. And then over time, as that drops off, your resistance reading is going to get higher according to this formula. Now, that time can depend on a number of properties. If you're testing two conductors, let's say in a piece of ripcord where you've got the two conductors close together and a long run, you're potentially going to have a lot more capacitance in that. And then you'd have to understand that you need to run a longer test to ensure that that capacitive leakage current is accounted for. Then we get to polarization absorption leakage current. That relates to the behavior of the actual insulation or dielectric material itself. When you actually have a current and have a charge pressure going through your insulation, it will actually polarize, and its level of conductivity or insulation will change and should improve within a period of time. Now, that period of time, again, can be within split seconds or a few seconds, or it can take longer. And if it takes longer, then typically you've got an issue with either moisture or contamination in your actual insulation, which is allowing for more leakage current. And that you can see in the time duration tests when you do insulation testing. And the beauty about these tests, especially as you're using direct current to do them, you can soon see a weakness when you start stepping up the pressure in a pipe or an electrical system. I demonstrated this in one of my previous videos. I had two pieces of wire spaced very closely together, but nonetheless, there was a little air gap in between them. And if I took a standard multimeter and put it on the two wires, the continuity tester couldn't see anything. If I measured the resistance, it said there was a high resistance, implying that there was no leak. However, when I got an insulation tester and applied a high voltage across those two wires, we then got a spark jumping across the gap and causing a flow of electricity, which then resulted in a measurable resistance level. As that leakage or jump of electricity to another conductive surface, which potentially is going to cause issues. So you might be able to see this, obviously, the slightest gap between those two wires is where they're almost touching. And that's obviously why we're not getting the continuity through them. If we pass 1,000 volts through there you go. Right, so let's try and quickly answer the question of what resistance reading do we want to see when we do testing of an electrical system. Now, ultimately what we'd like to see is an infinite resistance reading, but as I said, there is a natural leakage through insulation, which means you're going to have some current flow, so you are going to get some resistance reading. Now, on many of the meters, what you ultimately want to see is perhaps an over limit or an overvalue reading on the meter, and that means your resistance is high enough. Some meters will stop reading at above 1,000 ohm or 2,000 ohm, 2 mega ohm. But the rule of thumb, and this literally is a rule of thumb, and this changes between electrical systems, the appliance you're testing, if you're testing motors or switch gear. So you have to, that is where experience and understanding the manufacturer ratings for certain systems or wires comes into play. But the general rule of thumb is that if you're testing a system of, let's say, less than 1,000 volt, so let's say our household voltage systems, which whether you're in the UK or the US, obviously carry less than 1,000 volts. There you'd like to see a resistance reading of at least 1 mega ohm or greater. Once you start getting to systems of greater than 1,000 volts, and there obviously what you'd want to do, if you've got a system which is carrying 1,000 volts, you want to pressure test it or insulation test it at greater than 1,000 volts. So there you want to see at least 1 mega ohm plus 1,000 ohm, an additional mega ohm, for every additional 1,000 volts of test voltage that you use. So if I've got a 1,000 volt system and I decided to test it at 2,000 volts, I'd like to see at least 2 mega ohm of resistance. If I'm going to 5,000 volts of test voltage, then I'd like to see at least 5 mega ohm of resistance. But that's a general rule of thumb, and that can change, as I said, between the different situations. Right, before I start the next demonstration, I want to talk a little bit about safety. And as I said, even though I'm covering off some safety aspects here, I'm certainly not doing a full comprehensive coverage of what you need to consider. Generally speaking, for this kind of work, you're potentially going to be working in an area where you're going to be coming into contact with high energy systems. Even if it's in your household, you're going to go to your breaker box or your DB board in your house, there are nonetheless high voltages there and high energy. If you work in those areas without properly ensuring that you de-energize the systems, because that's what you need to do before you do any installation testing, you need to make sure all the systems you're testing have no energy flowing through them, no electricity. So they need to be switched off. People need to be informed of what you're doing. Jewelry needs to be removed. If you have jewelry or watches, nice bits of metal, while you have your hands inside a box, there may be a live conductor around which you just happen to touch, and that can be very costly. The other thing is ensuring that your tools and your leads in particular are all intact, there's no breakages in them, and ensure that when you're working in high energy situations, that your test probes are shrouded, and that goes for the same as your screwdrivers. If you're using screwdrivers near and around a DB board, you should have the shaft insulated, so you've only got the working tip which is exposed, so that again it accidentally leans over and touches an electrical component which is live, you're not going to get a shock or cause a short. With these probes, they have tips that can be lowered and raised. These happen to be a set of fluke probes. And many probes these days come with a cap which will reduce the exposed tip area to between 2 to 4 millimeters. And that is what you want to do to ensure, again, if you've got 2 probes and using 2 hands, which can be very dangerous, that again, they don't cross over and touch and short and release a big electric flash into your face, or touch something else which has got high energy and cause a high energy to flow through your meter, perhaps causing damage to equipment or yourself. The other electrical rule of thumb is to always try and work with one hand in your pocket. It's an old electrician's piece of advice to ensure that you don't allow a high current or high energy to flow through your hands and across your heart. You don't need much current to flow across your heart to cause an issue. For that reason, many of these testers allow you the capability of having a crocodile clip on the one end which you can clip to release your hand. You should then work with just one hand with your probe. Many of these testers will then also go to the point of having an actuating button on the probe itself. So you're not fiddling with the meter, but can concentrate on what you're doing, push the button on the probe, get the reading, and understand whether you've got an issue or not. These are important things to take into account. The next safety tip is to ensure that, again, your test equipment is working correctly. Now, as I said, the one thing you want to ensure is that any circuit that you're working on is de-energized. And you want to have something like a non-contact voltage probe or even a voltmeter to ensure that there's no voltage or energy there. And if you want to make dead sure things are working correctly, now I do this because I'm scared of electricity. I've got a non-voltage probe. If I know I'm going to be working in a DB board, I'll always go and test it first. I know it's working. I'll then go to the DB board and wander it around everything that I might be near to test that there's no voltage. I'll then come back again and test it to ensure that it was operational during that exercise. Next, you'll want to test your instrument to make sure it's operating correctly before you go into a high energy situation to ensure you're going to get the correct readings. Also remember that these meters can supply anywhere from 50 to 1,000 to 5,000 volts. It only does it at a very low current. However, as I said, if you pass a low current across your heart, that can potentially be fatal. To test this instrument, what you do is switch it on. The first test would be to have the leads open, push the test button, and what you want to see is an overreading or the top reading on your meter to show that it's got high resistance. In this case, 2.2 gigaohm. For the next test, you want to clip the leads together, test, and ensure that it's reading 0 ohm to know that your meter is reading 100%. Another piece of good advice is to actually have a pair of rubber gloves when you're going into a situation or a DB board where there could potentially be high energy. In this next example, I'm going to go through some of the test procedures that might be involved in portable appliance testing. So in this case, I've got an electric kettle which has got a stainless steel body, which could potentially be a danger if there's any of either the neutral or the live wire happen to be touching the body and someone touches this and then earths themselves. So in this case, what we're going to do, we've got the American plug, we've got the earth pin, a live pin, and a neutral pin. We want to test several things in this case. We want to ensure that there's no conductivity between all the conductors. So between the live to earth, the neutral to earth, and then from the neutral to the live or hot. You want to ensure that you've got a good grip so that it's not going to slip about and cause any issue that you have to try and reach and grab for it if it falls off. I'm then initially going to go to the neutral. I've got this set to 1,000 volts. Now you need to be aware that certain appliances will be damaged at these voltage levels. So when you do this testing, you need to ensure that any sensitive equipment, especially if you're testing an electrical system, is removed and unplugged from the electrical system. Items like light bulbs and dimmer switches can cause misreadings or false readings, and in some cases those items might be damaged. So here you go. So as you can see, between the earth and the neutral, I've got a greater than 2 gigaohm. So we've got no concern with the insulation there. But as you can see, the reading was immediate. Now I want you to note that before we get to our next example. Now I'm testing between live and earth. Greater than 2 gigaohm, immediately, no issue with the insulation there. Now we're going to test between the live or hot and the neutral. And again, greater than 2 gigaohm, no issue there. The next important test, in particular for pack testing, is we want to ensure that the earth is actually going to the body of the kettle. Because if it's not going to the body of the kettle, that could result in the earth leakage system not working correctly. So I've got the negative cable connected to the earth on the plug, and now I'm going to test against the body. And what we we're seeing there is almost 0 ohms, which is what we're expecting to see because we want to ensure that it's got a proper connection to the kettle. On this insulation tester, which happens to be the Fluke 1584, you can see it's got a test voltage level range which you can set. So if I push this button, it's going to cycle through from 50 volts, 100 volts, 250 volts, 500 volts, and 1000 volts. Now the general rule of thumb for appliances is that you want to apply, and perhaps if you're doing in lower steps, is an equivalent voltage. So let's say I was testing that kettle here in the States, so I want to test it perhaps at 100 volts. But there I'm not really applying a lot of pressure to see if there's any insulation issue. So ultimately you want to apply at least twice or 2.5 times the voltage rating. So in that case, I'd probably want to, if I was going to do a safe test, do a test at 250 volts on that kettle. In that case, I really wanted to see whether the insulation was in good order. So I wanted to apply the highest pressure or voltage test that I can do with this insulation tester, which is 1000 volts. But you have to be aware, some equipment that you test or some appliances that you test might be damaged at those voltage levels. Next, I'm going to do a test on this roll of wire. So I've got this ripcord.
So this is for the electrical insulation resistance testing. So when you are doing the electrical test, you also have to do this insulation resistance. That is why it's an upward loop impedance test. Upward loop is when the electrical current flow to the arc. So this is a connection between the active to the arc is an upward loop. So the upward loop testing that identified. The main reason for the upward loop impedance testing, which is often simply called the blue testing, is to verify that in the fault forecast in the electrical installation is sufficient current will flow to operate the fuse or the circuit breaker, producing the faulty circuit within the predetermined time. This means that when the electrical upward happens, the current will operate the circuit breaker. So this is the upward loop. So these are the connection of the upward loop. So this is the coil here, the load, and this is for the resistor incoming, this is the outgoing wire, and this is out. So that all the resistance around the R is the upward loop. So that there will be the ZS is going to be ZE plus R1 plus R2. So this is the upward loop. So that we have to measure the ZE, the supply to the equipment, and R1 plus R2 is between the equipment to us. So this is for the supply R1 plus R2. This is the ZE is the supply to the up to the equipment, and R1 R2 is a return, and there's a coming and return lines are impedance. So this is the upward loop resistance. So when you are testing the upward loop, this is for the diagram to show the upward loop. So one is terminated here, and another is connected to up, and then we have to drive, we measure the resistance. So this is the upward loop resistance measure. So one is connected at the end, there's a neutral combiner connected to up, and one is connected to active, and then we measure the resistance. So this is the connection of the upward loop impedance measurement diagram. So those are the equipment measurement diagram where to place at the neutral, and this is the measure between the up. So when the electrical fault happens, the current flow here go to up and go back to the equipment. So this is why that we have to do the test upward loop. So this is also the upward loop impedance testing diagram for the electrical socket outlet. So you have to view this upward loop impedance. How to measure? So you have to view this video.
Hi everyone, this is Andy Sutherland, Trade Skills for You, and in this video we're going to be looking at ZE testing. ZE, the part of the earth impedance path that is external to the installation, hence the little We're also going to look at the difference between ZE and ZS and dB, and I'm also going to show you how to test for IPF or prospective fault current. The purpose of the ZE test is to determine whether or not an installation has a sufficient amount of earthing. So in this diagram here, I'm showing the earth fault current for a TNS system. The main earthing conductor, which is here, coming from the distributor and connected to the board to put the or coming from an earth electrode or earth rod if this was a TT system. It has to be checked to make sure that it's continuous, there's no break in it, and also that this value here meets the recommended value as recommended in the on-site guide by the DNO itself. We'll look at those figures in a moment. But why is it so important to check? Well, let's just start here. In the event of an earth fault here, so we've got a line conductor touching an exposed conducting part. So the current is flowing through the exposed conducting part, it's being picked up by the CPC, which it's connected to, and then the fault current will flow down through the main. As this is a TNS system, it's flowing down a sheet of cable all the way back to the transformer, where it will...
Breakfast is when you rent somewhere to live and you buy...
You've got this, what is called an earth fault path. When the fault hits the consumer unit, the distribution board, the protective device should operate so long as the time taken for the current to flow around this loop is within a specified value. We need the resistance or the impedance of this path here to be a sufficient value in order for the protective device to disconnect within the correct time. So that's why we've really got to check that the earthing conductor from the distributor or going to our earth electrode is sufficient, doesn't meet those figures. So in order to do that, we have to disconnect it to test it. We don't want to be testing any other conductors. We might be getting parallel paths if we don't disconnect it. So I'm going to show you how to do that in a moment. But the area that we're going to measure, if you like, is this external section where we're measuring the incoming earthing conductor along with the incoming line conductor, and that is going to give us a value which is going to go on our certificate of ZE. This test has to be done at the origin of the installation, with the main earthing conductor removed and the installation safely isolated. I'm going to show you how to connect the meter to do this test. Just to recap, the reason that we're doing a ZE test is twofold. We want to make sure that there is an earth connection to the installation. Secondly, that the value, the ZE value, is equal to or less than the value determined by the designer, and those values quoted in the on-site guide by the distribution network operator. So here's the installation. This is the origin of the installation. So this is the distribution board or the consumer unit that is at the origin. And as you can see, we're going to disconnect the main earthing conductor. We have to make sure that the installation is safely isolated. Moving the meter would be very dangerous if we have an isolated installation. Once we've isolated, we can disconnect the conductor, clamp onto it, and then our other two leads on our meter go around the incoming useful containers, which obviously we store alive. Now, most modern meters, most modern meters or earth-folding meters have got 3 leads, so they need the neutral in order to conduct the test. However, some newer meters have only got 2 leads, so it would be a question of just reading your manufacturer's instruction with your meter as to whether or not you need 2 leads or the 3 leads. So the values that are quoted in the on-site guide by the distribution network operator are as follows. For a TNCS earthing system, we need a maximum ZE no greater than 0.35 ohms. For a TNS system, then the maximum value of ZE is 0.8 ohms. And a TT system, well, an earth rod, they recommend 21 ohms, but it can vary. And the on-site guide says that anything over 200 ohms may be unstable, so a TT ZE is going to vary. For the purpose of this video, we are now at the origin of the installation with metering equipment and views. Here is the main earthing terminal with the main earthing conductor coming from the DNO, and the earthing conductor connecting to the Earth terminal within the consumer unit. And it's at this point that I will remove the earthing conductor for the test. I need an incoming supply in order to do a ZE test, so I'm just going to use my approved voltage indicator. Earth terminal to incoming line, 230 volts. I just check that the neutral is dead. Yeah, back on the line. This also is a test to confirm supply polarity. I'll just show you where it goes on the electrical installation certificate. So it could be on page 1 or page 2, depending on which certificate you're using. But here you can see a little tick box, confirmation of supply polarity. So as we've just proved in the previous test, there's also a box on the schedule of test results in the top left hand corner. Once you confirm supply polarity, the test sheets and the main we should put a tick in that box as well to confirm that the supply polarity is correct. Now I'm going to remove the main earthing conductor from the earth terminal. Normally there would be lots of CPCs and maybe bonding conductors in here, so it's essential that I remove the conductor in order that that is just the conductor that I'm testing. I don't want any parallel paths. Get our meter, turn it to loop high setting, and then next our earth clamp to remove the earthing conductor. Notice how the installation is safely isolated. And then the next two probes, the line and the neutral. Make sure we've got a voltage meter and press the button. And ZE is 0.50. Now I'm just going to remember that because it's essential at this point that I put that earthing conductor back in. We must reconnect the earthing conductor immediately after the test. Never leave an earthing conductor out longer than is necessary. The minute you've done the test, put that conductor back in, tighten it up. So now we can write that on our electrical installation certificate, and again, either on page 1 or page 2, you will see supply characteristics of earthing arrangements in here. So this is the area that we're in, and here we have ZE, and in this box here we need to put the value, so it's just got a value there of 0.50 ohms. So we can drop a 0 and put 0.5. In that box there.
Might not get as high as the market was initially worried about, which would in turn increase the probability that
our ZE test was taken at the origin of the installation in the main Now, if we do an earth fault looping meters test anywhere else within the installation, other than at the origin, then there's going to be this part of the circuit involved. There's going to be an R1, R2 value to take into account here. Now, if this area of our installation was another distribution board, we would have ZE, we just measured at the origin, and then we would have the R1, R2 of any subname, which would consist of the line like you can see here. So this area in our installation could be another distribution board or consumer unit, and a test taken at this point would be what is known as a ZS test. ZS, as you will see in the on-site guide, is ZE plus R1, R2. It's this whole circuit that takes into account ZE as the origin, plus the R1, R2 of any subname to another board. That's going to be known as a ZS value. And on our schedule of test results in the top left-hand corner, you will see ZS and dB. I have to do a ZS at dB at the installation origin as well, so set my meter to high. This time the earthing conductor stays connected. Now, because there are no parallel paths here, I'm expecting to get the same reading, and in a domestic situation it would probably be the same reading here, but here we go. And there we go, 0.50 ohms, ZS and dB. On the schedule of test results for the distribution board or the consumer control unit at the origin, the top left-hand box there where you can see ZS and dB up here, this area here, this is where we now write that value. Now in this example, it was exactly the same as the ZE. However, we still write it on if it's the same. In a domestic environment, you can often do the same, or parallel paths connected, slightly lower. However, you just do the test as I've shown you, you write the value in this box on the schedule of test results.
Sentiment actually tapers as well through the year. 90% of financial officers cited difficulties.
The purpose of a prospective fault current test at the origin of the installation is to ensure that the amount of current flowing in the event of a fault won't exceed the rated value of the fuse. Now to do this test, we clamp onto the earth bar with all the earths, the bonding, CPCs all connected, and we're doing a ZS and a dB effectively like we've just done, 0.50. Now our meter will calculate for us what is known as this prospective earth fault current. Let's press the button and there we go, 486.6 amps. Now fault current is expressed as kiloamps, so in this case our prospective earth fault current, our PEMC, is 0.486 kiloamps or 0.49. Now we have to test how much current would flow in the event of a short circuit fault at the origin. And to do that we need to combine our earth and our neutral probes together. On some meters you can do this at the touch of a button. With the meter I'm using, you've physically got to make the joint between the earth and the neutral and put a probe on and now test between the incoming live tails, so the line and the neutral coming in. So this is how much current would flow in the event of a short circuit. So this is known as prospective short circuit current. Now when we press our button, we're going to get an impedance here first of all between the line and the neutral. So we're going to get a reading in ohms. Well, we don't need that for any certification, so we can just press the button. Let's have a look at the short circuit current. There it is, 408.9 amps or 0.40 or 0.41. Our IPF, our prospective fault current, is quite simply the highest of these two values. The value of IPF can now be written on our electrical installation certificate under the supply characteristics and earthing arrangements, where earlier we'd written our setting of 0.5 and it's just in the box above there where you can see IPF in kiloamps. So I'm going to round up our IPF of 0.486 to 0.49 and put it in the box there. This value of IPF can also be written on the top left-hand side of our schedule of test results, just underneath where we've written our ZS and dB reading of 0.5 in this area here. And so let's put in there our 0.49 and we confirmed our supply polarity earlier, so let's just make sure that we tick that box too. I've locked off this board further down the line to show how to do ZS and dB at a board that's not at the origin. So when we come to do our test, we just simply clamp on to the earth bar, nothing is removed, all the earths are in. Meter on the loop high setting if there's no RCB beforehand, and then onto the incoming line and neutral. Press the button, and this is my ZS and dB. And further down the line, so I'm getting 0.67 ohms. And now when I press the button, I'm going to get my prospective earth fault current, 0.368 kiloamps. I've now got to do my short circuit current here and find out which of the two readings is going to be the highest to get my fault current. So let's join the earth and the neutral again. As I say, some meters you can do this at the touch of a button. I'm going to do it physically with this meter. Earth and neutral leads together and then onto the incoming tails and the line neutral. And I'm going to press the meter, I'm still on loop high, press the meter, the first reading is going to be the impedance between the line and neutral, which we don't need, so I'll press my button. And there is my prospective short circuit current of 0.308 kiloamps. IPF is the highest of these two, so I'm going to be entering 0.368 on my certificate.
for my schedule of test results at this particular consumer unit, which is not at the origin, then I'm going to fill out this area here, ZS dB and IPF at dB. So the ZS at dB, 0.67. And notice how the IPF further down the line is reduced. As the further you go down the line, as the impedance increases, the prospective fault current decreases, which is why it's so important to do it at the origin, because that will be the highest value that will be measured in an installation. So the highest of my earth fault current and my short circuit current is going in that box there. I've just rounded it to 0.37, and supply polarity was confirmed earlier, so let's just give it a tick. So there we go, ZE, ZS at dB and prospective fault current testing. This has been Andy Summers of Trade Skills for You. Thank you for watching. For more information on all our
So this is this one we show about the for loop. For loops are impedance testing and the prospectus are for currents are testing. So this is a today's lessons are what I cover is I told you about the told you about the polarity testing. So that I give you the polarity testing definition and also the polarity testing procedure, visual checking, testing with the meter, and I give you the ones video regarding the polarity testing. The second things I talking about this insulations resistance testing. So resistance testing, also that I give you the video. So polar insulation testing resistance, also that I give you the insulation resistance testing video. The next one is the for loops resistance testing and prospectus short currents testing. So this is the also I give you the video. So this is the today's lesson. Next time I give you the testing for the correct polarity.